In the last chapter, we talked about using confidence intervals as a means of inference for a population parameter. So, for example, given a sample mean, okay, a statistic like a sample mean, we would make an interval for values that we thought would contain the population mean or the parameter. Same thing if we were given a sample median. We would create an interval for what we thought the population median might be. Or if we were given a sample proportion, like a p-hat, we would create an interval for what we thought the actual population proportion might be. This chapter is a little bit different. We are still using inference, but the inference that we are using here are called significance tests. What these tests are there for testing claims. So, for example, let's say that M&M or Mars Company says that 30% of all M&Ms are blue. Well, we may take a sample and see that we have 15% of our M&Ms are blue. Well, we can use a significance test to see if 15% is far enough away from the 30% that they claimed that we think maybe they aren't telling the truth. Maybe it's lower than 30%, and that's why we have such a low value. Or the other side of that is maybe it really is 30% and we were just unlucky enough to get one that only had 15% just by random chance. There are always two sides to significance tests. One is that the claim really is unfounded, and that's why you have a value for your sample statistic that is so far off. Or the claim is very true and your value is so far off because of just random chance. Because while it doesn't happen often, it probably happens some. Okay, so let's look at this example. I'll give you a second to read it for yourselves. Okay, so two explanations for why this sample proportion, okay, this p-hat here, is so high. Because what we're asking is this high enough to say that the true proportion of all couples who kiss the right way is greater than 50%? Okay, or the proportion is greater than 0.5. So one explanation is that yes, okay, P really is greater than 0.5, and our p-hat is just representative of the sample. Okay, the other explanation is that P is actually, okay, the true population proportion is actually less than 0.5, and our p-hat is so high just by random chance. It just so happens that that reporter saw that many couples just by random chance. Okay, these are always your two explanations. Okay, and you're looking to try and decide which one is more plausible. Is it that the claim really is true and you have the evidence to back it up? Or is it that the claim maybe is not true and your value just happened by random chance? The way that we decide which of the two is more plausible, that's where the significance test comes in. It's always one of these two explanations, and we are just trying to use the significance test to determine which one is the case. Okay, so what is the basic idea behind a significance test? The basic idea behind a significance test is that I'm going to look at the probability of getting the value that I have as a sample statistic, or something more extreme. And I'm going to do that assuming the claim is true. If the probability that I would get that value if my claim about my proportion or my population parameter is true, then I can assume that the claim, if my probability is high, then I can assume the claim is true. However, if my probability is really low of getting that value, if that claim is true, then the claim's probably not true. For those of you who have taken pre-cal, you may have talked about like indirect proofs, like assuming something is true or false until you prove otherwise. It's kind of the same thing here. We are going to assume the claim is true, and then we're going to look at the probability of getting a statistic of that value. And when I look at the probability of getting a statistic, that is where my sampling distribution comes in. So once again, we're talking about the things from chapter 7. Okay, I'm going to be using our sampling distribution and not the population distribution. And if my probability of getting that certain statistic or more extreme is really high, then probably that happened because the claim is true. However, if it's really low, and in this case we typically use 0.05 as a cutoff, but we'll talk more about that later. If my probability is really low, then that claim probably is not true because there's such a low probability of my statistic occurring if that claim were true. So the first two steps are the first step, I guess, in performing a significance test is stating your hypotheses. You almost must have hypotheses in order to have your significance test. Okay, and there are two types of hypothesis. The first one is null. Null is represented by H sub 0, and it is a statement of no difference. So if in my kissing example, I wanted to say that my claim is the proportion of couples who kiss the right way is above 50%, then my null would be that P is equal to 0.5. And I would write it just like this, H sub 0 colon P is equal to 0.5. That's my statement of no difference. If I'm trying to say it's above 0.5, 0.5 is like the boundary. Okay? Typically, if you're dealing with proportions, it's going to be 0.5 because no difference would mean half do one thing, half do the other, 0.5. Okay, the alternative one is HA, and it follows the claim. So in this case, my statement of no difference is equal to 0.5 since I'm trying to claim that more than half of couples kiss the right way, P is greater than 0.5 because I follow my claim. Okay, common mistakes when stating hypothesis. Okay, the first common mistake is that students use statistic notation, okay, sample notation, like X bar and P hat. Okay, we're going to know X bar and P hat because those are values from my samples. You must always use the parameter notation like mu and P. Use the notation of things that you know. So use P and mu, not P hat and X bar. Okay, you know these values. It's these you're trying to find out if they exist or not. And another common mistake is that students try and use the data. When you're making a hypothesis, that means you haven't collected your data because just like in science, hypotheses are the very first thing you do. So use the wording of the question to form your hypotheses, not the data. Because if you use the data, then you're cheating because you're kind of seeing the answers before you ask the question. Okay, so there are a couple different hypotheses that you can use. One-sided hypotheses for alternatives just mean that they go one direction. So greater than or less than. So if my null is equal to, my one-sided ones are it's the value is less than or the value is greater than. A two-sided one is when I say not equal to. One-sided ones are better. So if you can tell from the wording of the question which direction to go, then choose the one-sided. If you can't, then just choose the two-sided one. Okay, and we'll talk about how this one is different from that one. But as far as wording goes, for one-sided, your words are going to be things like, is it greater? Is it less? Is it smaller? Is it bigger? Directional words. For this one, it's if, like the question just says, is it different? If it doesn't specify a direction, then that's when you want to choose the two-sided. So here, Mike is an avid golfer who would like to improve his play. A friend suggests getting new clubs and lets Mike try out a 7-iron. Based on years of experience, Mike has established that the mean distance the ball travels when hit with his old 7-iron is, and this symbol is supposed to be right over here, 175 yards with a standard deviation of 15 yards. He's hoping the new club will make his shot with a 7-iron more consistent, which means less variable. So he goes to the driving range and hits 50 shots with the new iron. Describe the parameter of interest in this setting. Well, I can see from this right here, I'm wanting it to be more consistent. Well, what thing measures consistency? Okay, that's some measure of spread, which in this case has to be the standard deviation. So my parameter of interest is that I am interested in the standard deviation of his shots, okay, with the new club. And so what would the parameters be? Okay, well remember the alternative one is always going to be no difference. So if it's no difference between this club and the club before, then the standard deviation is going to be 15. We are looking to make his shots less variable, which means we want to test out the hypothesis that based on whatever sample standard deviations we get out of these 50 shots he's about to shoot, we're gonna try and see and test the claim that his new club has a standard deviation less than that. Okay, so check your understanding on page 532. Take a moment, look at the questions, check your understanding. Here are the answers, so you can pause this until you've got them answered. Okay. Hopefully you did not have any problems with those. So let's talk about p-values. What is a p-value? Okay, the p-value is the probability the statistic will occur. So what is the probability that given our claim, the statistic we have will occur? Okay, you have been finding p-values all year long, and we just haven't called them that. We've just called them probabilities. But anytime we have found the area under a curve and we've said, okay, what's the probability that x is going to be greater than 4? Okay, and we've had a mean, we've had a standard deviation, we found a z-score, and we found this probability, and we say this probability is equal to some number. Okay, that number right there, the area under this curve, that's a p-value. That's all it is. Okay, you've been finding them all year, now we're just giving it a specific name. Anytime I ask for a p-value, that means I want the area under the curve. Okay, I want the probability that that's going to happen. So a lot of times you'll see the notation written like this. So for the kissing example, okay, this is the p-value represented as the probability that the sample proportion would be greater than or equal to 0.669. And we know this line from chapter 5, given that the claim p equals 0.5 is true. Okay, that's something about significance tests. We always assume that the null is true. Okay, that's what we're testing. The fact that the null is true. So what is the probability that I'm going to get a p-hat value greater than or equal to 0.669 given that p is really equal to 0.5? And whenever I do that, and I calculate it and I find a z-score, okay, and I can do that here. There are some conditions we're going to have to check, but generally I would calculate a new standard deviation here. I would assume that my mean of p, okay, my mean of my p-hats was equal to the 0.5. I would say the standard deviation of p hat is equal to the square root of 0.5 times 1 minus 0.5 divided by whatever the sample size was. And then I would find my z-score, and then I would look to my curve, its proportions, that's why we use a z-score, and I would find that probability. Okay? And what it means is it's the probability that, okay, if p really is 0.5, I would get a sample that has a sample statistic p hat greater than or equal to this value. And if it's a big number, if my p-value is large, like 0.2, so like 20% or 15% or 16% or 60%, then I would say, oh, okay, that's pretty likely that that would happen. And if my p-value is small, like 1% or 2%, I say, wow, that's so unlikely that that would happen that maybe this really isn't the true value. Maybe it's something higher than that. And that's why I got such a large value for p hat. Okay, so here we have Mike. Mike's testing a new 7-iron, and we have his hypotheses here. And based on 50 shots with this new 7-iron, so they're telling us N right here is 50. Here's his new standard deviation. So a significance test using the sample data produced a p-value of this. So what does that p-value mean? It means that if the true standard deviation really is 15 yards, there is a approximate probability of 0.002 that the sample standard deviation would be 10.9 yards or more extreme. So in this case, since we're looking for 15 and that's less than, we say or less. That's what the p-value means. If 15 here is the true value, if the null is true, then this is the probability that we are going to get that value or less. Okay? So does this provide convincing evidence against the null hypothesis? And we say yes. Because the p-value is very small, random chance is not a plausible explanation. We just say that the probability that that would happen is too small. We call this statistical significance. So there are two possible conclusions for a significance test. Okay? One is that we reject the null, which is what just happened there. If your probability is so small that you say, oh, this is probably not going to happen just by random chance, therefore my null is probably wrong. Okay, so one conclusion for the significance test is my p-value is low, really low. I'm going to reject the null. However, on the opposite of that, you would think that you would accept the null, but that's not the case. You have to use the words fail to reject. Because all you're saying there is not that you accept and you say, oh, this must be the value. Basically, you're saying, I have a lack of evidence to prove otherwise. I'm saying that my value here has a probability large enough of happening that that could be correct, but you don't know for sure. So if your p-value is not low, then your wording has to be fail to reject the null. Never say accept. Okay? Oh, and that's a common error. Never say accept. Never say you accept the null. Okay? You always need to say fail to reject, because what it means is that if your p-value gave you a value large enough to say, okay, well, this could theoretically happen if this were the true value. Okay? If whatever this sample statistic here Okay, my p-value is large enough that theoretically it could happen if that were the true value. However, that doesn't mean it has to happen that way. It could also happen if like this were the true value, or if this were the true value. Okay, so you can't actually pinpoint what the true value is. You can just say whether or not you have evidence to reject the claim that's being made. Never that you have the evidence to accept it. Okay, and what a significance level is, it has a symbol, alpha, the Greek letter alpha. Okay, a significance level is a value for our p-value that is our cutoff. Okay, throughout the year we've been using like 0.05. So we say below that value and we're going to reject it. Above it we're going to fail to reject. Okay, and we call the results of a study statistically significant if they're below that p-value range, if they're below the cutoff. Okay, if they are less than alpha. Anytime that we can reject the null, that's when we say that the results are statistically significant. So if you see that when you are, reading some article or looking in a journal or a newspaper, if they say their results were statistically significant, that means that they had a p-value low enough that it was below their alpha and they could reject the null. Okay, so here, for a second semester project in AP Statistics, Xenon decides to investigate whether students at his school prefer name brand chips or generic. Okay, so he randomly selected 50 students and had each student try both chips in random order. Overall, 34 of the 50 preferred the name brand. So he performed a significance test using the hypotheses. The null p is equal to 0.5 versus p is greater than 0.5, where p is the true proportion of students at his school who prefer the name brand chips. Okay, and notice that this 0.5, because it's a statement of no difference. If it doesn't matter what chip they like, then that's half and half. Okay, his resulting p-value was 0.0055. What conclusion would you make at each of the following levels? If our alpha level here is 0.01, I need to say which one is larger. And here, if I'm looking at this, 0.01 is larger than 0.0055, which means alpha is larger than my p-value, which means I'm going to reject the null and choose in favor of the alternative, which means I have convincing evidence that the true proportion of people at Xenon's school who prefer name brand chips is larger than 0.5. However, if I look at this alpha level, 0.001 is less than 0.0055, which means I fail to reject the null, which just means I do not have convincing evidence to say that more than half of the students prefer name brand chips. Okay, so what should be considered when choosing a significance level? There are a lot of things that go into it. One thing that goes into it are errors. There are a couple types of errors, and they're going to be on the next video, and we're going to talk about those on the next day. But significance level plays into the error sum and valuing which type of error you'd be more willing to make. Also, just your field of study. For instance, in the medical field, statisticians usually use an alpha level of 0.1 versus in the field of education where they sometimes use it in 0.05. You may see a 0.025. It just really depends on the field of study. Psychologists may have a different alpha value, and scientists may have a different alpha value than educational researchers or people in the medical field. So that plays a large part into it as well.